So we ran out of time in class, but I wanted to make sure we had a chance to go over incline surfaces. So what do we do if our surface is not horizontal? The majority, maybe all of the problems we've done so far have occurred on a horizontal surface or a vertical surface, I guess. But we need to be able to deal with inclines or ramps. So we don't really do much differently. Just like we had to redefine our coordinate system for an Atwood's machine, we have to redefine our coordinate system on an incline as well. And here's why. If I think about a block of mass m sitting on a ramp at an angle theta to the horizontal, the only force right now we know that doesn't depend on the incline is the force of the Earth's gravity, the weight. The Earth pulls it straight down towards the center of the Earth, regardless of the angle. So weight equals mg is straight down. If we look at the other forces acting on the block, though, we've got the normal force. Normal forces are always perpendicular to the surface, so that must make a right angle to my ramp. Um, and then maybe not, we would have friction. Friction could go both ways here. If I'm pushing a block up the ramp, then friction would be going down the ramp. If we let the block naturally slide down the ramp, then friction would be going up the ramp. And that's usually the way it works. So this could be friction going up the ramp. So if you look at those two forces, the normal force is always perpendicular to the ramp. The friction force is always in the direction of the ramp, since the ramp kind of dictates the direction of motion and friction opposes motion. Then really it's the weight that doesn't really fit this mold. So when we determine direction for an incline, rather than saying our typical, you know, x and y directions, we're just going to tip that coordinate system, and we're going to say forces that are perpendicular to the ramp versus forces that are parallel to the ramp. So perpendicular and parallel are synonymous with y and x. So that means we're going to do something a little different because the normal force is already perpendicular. The friction force is already parallel. So it's the weight vector then that's going to need to be resolved. So when I resolve my weight vector into two components, then this is where it starts to feel a little strange, because the weight vector is actually the hypotenuse of this triangle. When I break it into its components, there is a component of the weight that is pulling it against the ramp, right? The perpendicular component. We could calculate that with mg cosine theta. The nice thing is if I know the angle of my ramp theta, when I resolve that, that's a similar triangle right there, and that's also the same theta. And then the component of the weight that pulls the block down the ramp is the parallel component of the weight, which is mg sine theta. It makes sense if you think about it, because if the ramp were at 0 degrees, so think about it, if theta was 0 degrees, the acceleration would be 0 because the block's parallel component of the ramp would be 0. There would be no component of the weight pulling it down the ramp. If the angle was 90 degrees, then the parallel component would be mg. mg sine of 90 would be mg times 1 is the full weight. So ramps effectively dilute the acceleration of gravity from 0 on a flat ramp to g on a completely vertical ramp, and everywhere in between. So let's look at how we might apply this then. So again, in this situation, if we have, let's say in this case, we have the force of friction. So I've got my force of friction here, and I've got my normal force here. So when I resolve my weight vector, and you do need to practice this a little bit because it doesn't come really naturally. If I just look at my normal force, it's the perpendicular component of the weight that's going to counteract the normal force this time. So another example of when the normal force does not equal the weight, it equals the perpendicular component of the weight. And then here is the parallel component of the weight, and that's what's pulling it down the ramp. So if my parallel component of my weight is greater than the peak static friction force, then this block will accelerate down the ramp. Likewise, for kinetic friction, if the parallel component of the weight is equal to the kinetic friction force, it will slide down the ramp at a constant speed. If it's greater, it will accelerate down the ramp. So how do we solve problems like this? I picked a couple out of your WebAssign. Um, so we'll start out with one with no friction. A crate weighing 596 newtons is resting on a plane inclined 25 degrees above the horizontal. Calculate the magnitude of the acceleration ignoring friction. So we're going to ignore part B as well because that's simply kinematics. So if we draw this situation, I've got an incline, I've got a crate sitting on my incline, and that incline is set at 25 degrees. So we want to do our free body diagrams like always. So I have my normal force and my weight. The important thing here is we recognize that it's my weight vector that's going to be broken down into a component that's balancing out the normal force and then the component that's pulling it down the ramp. So that's the force that's going to pull it down the ramp. So looking at Newton's laws, Newton's second law, the sum of the forces in the perpendicular component are going to equal 0 because the block is not going to be accelerating off of the ramp or down through the ramp. So that means the normal force we can call the positive direction off of the ramp minus mg, and remember this is theta, it's the same theta, so that's 25 degrees, mg cosine theta has to equal 0. So in other words, it's what we've said. On a flat surface, the normal force equals mg, because what would cosine theta be on a flat surface? Cosine of 0 would be 1, right? So on a flat surface, the normal force is equal to the weight. But on a horizontally vertical surface, then the parallel component of the weight is equal to the net force down, mg. So n equals mg cosine theta. I don't really need that for this problem because there is no friction. But again, when we get to the friction, that's going to be important. Over here, though, the sum of the forces that are acting along the direction of the ramp are going to equal mass times acceleration down the ramp or up the ramp. So we only have one, right? The only force that's kind of pulling this thing down the ramp is the weight component that is down the ramp. So mg sine theta has to equal mass times acceleration down the ramp. M's cancel out, and my acceleration is g sine theta, right? It's diluted gravity. Sine of 0 is 0, sine of 90 is 1, so I have a value for acceleration on a ramp anywhere between 0 and 9.8 meters per second squared down the ramp. The mass cancels out, which shouldn't be surprising. If I drop two objects, they both accelerate due to gravity regardless of their mass. If I slide two objects down a frictionless ramp, they're both going to have the exact same acceleration down the ramp. So that's an easier problem. There's no friction there. So I could just plug this in. Calculate the magnitude of the acceleration. Well, the mass here, or the weight, doesn't really matter. The acceleration would just be equal to 10 times sine of 25 degrees. Right? It's a relatively small angle. I know that sine 30 is 1/2, so a 30-degree incline would give me an acceleration half of g. So I'm going to be somewhere a little bit under 5, probably 4 meters per second, 4 to 5 meters per second squared here. Okay, so now let's look at an example where there's friction. So basically the same setup here, a 57-kilogram person on skis, right? So here's my ramp. What would a guy on skis look like here? Kind of like bent knees. There's his poles. Pretty good. So a guy on skis, 30 degrees. This time we now are told that there is a coefficient of friction between the skis and the snow. If you're told there is a coefficient of friction, then you're being told that there is friction. So I have to think about friction this time. Let's go ahead and look at the forces. If we do a free body diagram for my skier, I've got his weight is pulling him straight down. The normal force is acting perpendicular to the ramp, and friction is opposing that motion down the hill. So there are three forces there. So when I resolve this, again, the only force that needs to be resolved is my weight. So I have a parallel component and a perpendicular component, and I have the same angle there as I do for my hill. So Newton's second law says that the sum of the forces perpendicular are always going to be equal to 0 because there's never going to be acceleration in the perpendicular direction. So again, the normal force minus mg cosine theta has to equal 0. So the normal force is the parallel component of weight. That's almost always going to be true unless I have some other ropes or tension on there. Now here's where it gets a little interesting. If I go to the other side though, the sum of the forces acting parallel to the surface of the ramp must equal mass of the guy skier times the acceleration down the ramp. So I have two forces now. So normally, again, we don't have up and down or left and right. I kind of have both, but I normally just pick the direction of motion to be positive. So I'm going to say down the ramp is positive. If you want to call up the ramp positive, it doesn't really matter as long as you use the right signs. But since he's accelerating down the ramp, I'm going to leave A positive. So I'm going to say mg sine theta minus the friction force has to equal the mass of the skier times his acceleration. This is where the perpendicular information is important because I do know a new relationship here. Friction force is equal to the coefficient, this would be kinetic because he's sliding, coefficient of kinetic friction times the normal force. And the normal force is not equal to his weight. It's equal to the perpendicular component of the weight. So that means the friction force is equal to mu mg cosine of theta. Okay? So that's the new part to these problems is we're going to be putting friction and inclines together. So that gives me a value when I calculate here, mg sine theta minus mu mg cosine theta equals ma. Once again, the mass of the skier doesn't even matter. So they gave it to you, but don't freak out when they don't give it to you, because if you work it all the way through, if m is in every single term, then it cancels right out. So we're looking for the magnitude of the acceleration, so I can solve this. A equals, so remember what we said before, if there's no friction, it's g sine theta, but if there is friction, it's going to be a little bit less, so it's minus mu g sine, sorry about that, mu g cosine theta. Okay, so some new physics there with a lot of old physics. We're still doing them the same way. Now, one more interesting application here is, let's say that I have a incline. Let's put a ramp there. And I'm going to put a box on that ramp. And let's lock those two things together. Not lock them, but let's group them. Okay, so that means now, so let's say that at that angle, whatever that angle is, that block doesn't slide. So remember, in order for something to slide, it has to overcome this force of static friction. So static friction is less than or equal to mu times the normal force. So I have two surfaces, so mu is not going to depend on the angle, but the normal force does. So there must be some angle. If I start tipping this thing, then eventually, let's say right there, right there, I'm going to find that that's an angle at which the block Sorry, trying to get these separated again. Ungroup. There we go. So at that angle, when I put a block on this angle, it starts to slide. So that's a special angle, so we're going to name it. We're going to call that the critical angle. Critical angle is the angle at which right? So that's the equal sign right there. So we're going to say at the critical angle, we've met that force of static friction. So can we use that angle to help determine what the coefficient of friction is? So we can rewrite this coefficient of friction as a ratio of friction force to normal force, right? So let's do our free body real quick. We have the force of mg down, normal force there, friction force there. We're resolving the weight into two components. There's this critical angle right there as well. mg perpendicular, mg parallel. So when we write this out, if we look at this as equilibrium, in other words, we've just met, the block is at rest at, 32.999999999 degrees, and when I hit 33 degrees, boom, the block starts to slide. So we have just met this static friction, peak static friction force. So we could say that the sum of the forces down the ramp equals 0, and the sum of the forces along the ramp just broke 0. So I can say at 0, this is going to be the maximum point, the maximum angle at which it won't slide. Then that means mg sine theta minus mu mg cosine theta has to equal 0, right? Because still up here, we're saying normal force minus mg cosine theta equals 0. So the normal force equals mg cosine theta, just like before. And where are we? Friction force equals mu times the normal force. So the friction force equals mu mg cosine theta. Well, at that critical angle, let's put the little c's in there because this isn't all the time. This is at this special angle. Then mg sine theta must equal mu mg cosine theta, right? Solving for that equation. M cancels out, M cancels out, G cancels out, G cancels out. Mu equals sine theta over cosine theta. Well, what's sine theta over cosine theta? Tan theta. So that's a pretty neat little derivation that if we could find the angle at which something starts to slide, tangent of that angle is another way that we can find the coefficient of, or the peak coefficient of static friction. So that comes in really handy sometimes, especially in the lab when you're trying to figure out the coefficient of friction for something. If you can tip that surface and you can find that angle, that's always a nice way to find the coefficient of friction from that angle. So hopefully this will help you on those web-assigned problems. When we come back, we'll do a quick little review, but inclines will be part of our next test, which is coming up around the corner. So make sure you review this. Go back and look at the web-assigned problems if you've already done them, and make sure that you can kind of incorporate some of this new stuff. Have a good break. Make sure if you've got questions, you can email them over the break. Try to get this stuff sorted out so that we don't have to take any steps backwards when we come back.